Similar to numbers or vectors, we can perform operations on matrices. For example, we can add two matrices together. Okay, so let's let A and B both be two m by n matrices. So they have the same number, they have the same dimensions, same number of rows, same number of columns. Okay. We're saying A is equal to this matrix here. So the entries of A are A sub ij. Okay. Similarly, the entries of matrix B are B sub ij. So then to take the sum of the matrices, to add them together, we're going to take each entry from matrix A and add it to the corresponding entry in matrix B. They come from the same row and the same column. Okay, that's going to be the entry in the ith row and jth column in the resultant matrix. So let's do a quick example. Let's take a matrix 1, 3, 5, 0, negative 2, 4. And let's add it to negative 2, 0, 1, 3, 5, 8. So according to the definition, to add two matrices together, the entry in row ij is just going to be the ijth entry in matrix A plus the ijth entry in matrix B. In other words, we're adding this pretty much exactly the same way as we did vectors. We're just going to add corresponding entries together. So for the first row, first column, I'm going to take the first row, first column entry of the first matrix and add it to the first row, first column entry of the second matrix. 1 plus negative 2 is negative 1. And continue doing that. First row, second column of the first matrix plus first row, second column of the second matrix gives me the first row, second column of the resultant matrix. 3 plus 0 equals 3. And I'm going to keep on doing that. 5 plus 1 equals 6. 0 plus 3 equals 3. Negative 2 plus 5 equals 3. 4 plus 8 equals 12. Okay? The properties of matrix addition are just like the properties of addition that we're used to with numbers, but also with vectors. Very similar. We have the commutative law of addition. If I take matrix A and add to matrix B, it's the same thing as taking matrix B and adding it to matrix A. We have the associative law of addition. If I'm adding three matrices together, A, B, and C, it doesn't matter if I add A and B first together or B and C first together. We have an additive identity. There is a matrix so that if I add any matrix to it, I get that same matrix back. Okay, we call it the zero matrix, and as the name implies, it is the matrix of all zeros. All the entries are zeros. And we have an additive inverse. Okay, so if I have a matrix A, there's a different matrix that I could add to it. We're going to call it negative A, so that when I add them, I get the zero matrix. Okay. Now I'm not going to go through and prove these. They follow very similarly to the similar laws for vector addition. And they follow because we have these properties when we add numbers together. Okay? And then another operation that we're going to be familiar with from our time with vectors is scalar multiplication. We can scalar multiply matrices just like we do with vectors. So if I have a matrix A with entries A sub ij, and I multiply matrix A by some scalar value k, then the effect is multiplying every entry in matrix A by that scalar k. So if I have some matrix 2, 3, 4, 1, and I multiply it by the scalar negative 5, I'm just going to add each entry in the matrix, or multiply each entry in the matrix by scalar -5. So 2 times -5 is -10. 3 times -5 is -15. 4 times -5 is -20. And 1 times -5 is -5. And the same properties that we're used to with scalar multiplication, they hold for scalar multiplication of matrices. So we have the distributive law. The scalar multiple distributes. And we could do it the other way around. If we're adding two scalars together and then multiplying by a matrix, we could distribute the matrix in. We have the associative law for scalar multiplication. If I'm multiplying two different scalars by a matrix, it doesn't matter if I scalar multiply one of the scalars first, then the other, or if I multiply both the scalars together first, then perform the scalar multiplication. Okay? And then multiplication by 1. If I multiply any matrix by 1, I just get the same matrix back. Again, these properties, I'm not going to prove them. They're very similar to what we did to vector operations, and they follow because these laws hold for when we just multiply numbers together.